Hello everyone, on today's class we're going to go through the heat diffusion equation, which is the most important equation in conduction. This is chapter 2, and it's basically covering a two-dimensional heat transfer. In this course, we'll only cover as far as two-dimensional. We'll assume the z direction to be 1 unit length, but let's go ahead and start with a simple material balance to drive the equation of the heat diffusion equation. Okay, so if we start with a small differential element of the solid, and in that element there's heat transferring into the element from the x direction, we'll call that qx. It's also leaving the x direction as qx plus dx. The dimension for this differential element is dx for the x-axis and dy for the y-axis. So what the heat leaving is qx plus that distance there. Okay, so there's also heat transferred in the vertical direction, which is referred to as qy, and there's also heat leaving in the vertical direction, that'll be qy plus dy. There's energy generated inside the differential element and also energy stored. Okay, so to start off with our material balance, we need to first focus on our inlets and outlets of heat transfer. So for example, qx, we'll start with that. Qx, we know that the heat is transferring into that differential element by conduction, covered in chapter 1, and that will be negative k times a times dt over dx. And the reason behind the differential is because temperature is a function of x, y, and also z, but we'll assume z to be 1 unit length. So anyway, the area that's being used here is the area normal to the heat flow. So the heat flow is flowing in the x-axis. The area normal to it is the y-axis times the z direction, because if we assume the differential element is like that, okay, we're assuming this to be 1. This z direction to be 1. So therefore this area will equal to dy times 1 dt over dx. That's your heat flow in the x-axis. Same thing with your heat flow in the y-axis. qy will equal negative k a times dt over dy. The area used in this equation is the area normal to the heat flow. So the heat flow is in the y direction. The area that's normal to it is the y direction. Therefore, qy equals negative k times dy times 1 unit z, which we'll assume it 1 unit towards you coming out of the screen, okay, times dt over dy. Okay, now something is, yeah, this is dx, sorry, this is dx. Okay, now these are both our inlets to the differential element. Our outlets is qx plus dx, which is basically qx plus the differential of qx in terms of x. Okay, same thing with our dy, qy plus dy equals qy plus the differential of qy in terms of dy. Okay, so we're going to substitute the value of qx here and here. Also the values of qy here, and here. Okay? Therefore, qx plus dx will equal to negative k dy dt over dx plus differential of qx, which is that, times dt over dx. Okay, dx in terms of dx. Now same thing for q, heat flow in the heat leaving from the y direction, which is qy plus dy. It equals to qy right there, which is negative k dx dt over dy, plus the differential of qy in terms of dy, negative k dx dt divided by dy. Okay, don't worry, most of these terms are common, so they're gonna cancel out later. You'll notice that in the energy balance. See, like for example, this here and this here and this, they're both repeated terms, so they'll cancel out later and it'll be more tidier than this. Another variable we need to take into account is energy generated, which equals to q dot, which is the heat flow per unit volume times the volume times the volume. The volume equals to dx times dy times dz. dz is assumed to be 1 unit length. Therefore, volume equals dx dy. Therefore, energy generated equals q dot times dx dy. Okay? Energy stored equals mass times Cp delta T over T. This here is temperature. That is time. Okay? Now, we know that density equals to mass. We're trying to change one of these variables in terms of dx dy. Okay? So we know that density is mass over volume. Therefore, mass equals density times volume. Therefore, mass equals density times, this is your volume, dx dy. You can substitute that into the mass. Therefore, energy stored equals density times dx dy Cp delta temperature over delta time. Okay, now we have all our variables ready and we can perform an energy balance. The energy balance looks like this, if you remember from the previous class, which is energy entering the system minus energy leaving plus energy generated will equal to the energy stored. Okay, now energy flowing into the systems, if you remember, are qx plus qy. Those were the energies going in. The energy leaving is qx plus dx and qy plus dy plus energy generated, which is q dx dy, will equal to energy stored, which is density times dx dy Cp delta time over delta temperature over delta time. Okay, now we can enter these values that we found up here. Right there. These are the inlets and these are the outlets. So let's go ahead and do that. Just gonna pause the video here, input these variables and come back. So as you can see here, I inputted the variables from above. These are the inputs. Okay, the heat flow flowing in to the system. This is the heat flow flowing out, and this is your generation and storage. So as you can see, there's some repeated terms such as this here and this. If we multiply this negative inside the bracket, it'll be positive here and positive there. Okay, same thing here, multiply it here and here, positive, positive. Okay, so we can see that there's a change in signs between this and that. Therefore, these two can cancel out. Same thing here and here. That can cancel out. Okay. Now we can write what's left, which is differential in terms of dx. If we move the k outside as a constant, we'll be left with dy dx, this dx here, times dt over dx. You know what? We can cancel the dx dy's right away. There's a common factor which is right here, dx dy, that's repeating in every term. In this term, there's a dy here, dy dx. So let's cancel those, dx dy, dx dy, dx dy, dx dy. So we'll be left with k. We'll take it outside and use it as a constant. Second differential of temperature over second differential of x. Okay. Plus this here and this. There's two differential that will make it second differential of temperature over second differential of y. And I forgot the k. Plus k. Plus q dot equals to density Cp delta temperature over delta time, d temperature over d time. Okay, now we can get rid of that k by dividing by k on all terms. We'll be left with second differential of temperature over second differential of x plus second differential of temperature over second differential of y plus q dot over k equals density times Cp over k times dt over d time. And from the previous class, we covered that the thermal diffusivity is k over density Cp. So therefore, this term here could be referred to as 1 over thermal diffusivity. Okay, so we'll rearrange it. Plus second differential of y plus q over k equals 1 over thermal diffusivity times dt over d time, and that is your heat diffusion equation for conduction. This equation here is used to find the temperature distribution throughout the solid, and in order to do that, there is initial conditions and boundary conditions that need to be involved when solving this equation. So for example, the first initial condition that needs to be considered is when temperature as when x is equal to, when finding the temperature, x is equal to, x could be any x at any point, at any y, and temperature equals 0. That will be your initial temperature, meaning that at any point and any time in the solid, okay, at any point of x or y, at time 0, that is your initial temperature. Okay, for boundary conditions, the first boundary condition is constant surface temperature, meaning when finding temperature at x equals 0 and at any time, that temperature is your surface temperature. So for example, if we take a solid, differential solid, and at x equals 0, at this point here, okay, this temperature at the surface, that is your T surface. Okay, second boundary condition is constant heat flux, meaning if we have a solid, okay, and a heater is facing that solid, is being targeted to that solid, okay, the heat flux is constant throughout the solid, therefore the heat hitting the surface will equal to the conduction flowing into the solid. Therefore, QS, the heat on the surface, will equal to Q conduction, which is negative K dt over dx at x equals 0. Okay. The third boundary condition is perfectly insulated. Insulated, which means that your QS, your heat flux is 0. Okay. Meaning that, for example, your water pipes in the basement, they could be insulated, but they're not perfectly insulated. Just because a system is insulated, that doesn't mean it's perfectly insulated. To be perfectly insulated, that means your heat flux is 0 or close to 0. If it's close to 0, we can also assume that to be perfectly insulated, and we call that term is adiabatic. Okay. Therefore, if your heat flux is 0, therefore negative K dt over dx at x equals 0 or any point equals 0. Okay. Your fourth boundary condition is convection on a boundary. On the boundary. Okay? Which is, for example, if you have a solid, right, and you have a fan blowing into the surface of the solid, that's not constant surface temperature. It's not constant heat flux. It's convection. Therefore, your convection heat flux will equal to the conduction heat flux entering. So, for example, your convection heat flux flowing in will equal to the conduction heat flux flowing in. The convection formula that we covered in the previous class, which is H T at x equals 0, or also referred to Ts, minus T infinity, which is the temperature of the surrounding, will equal to negative K dt over dx at x equals 0. Actually, it doesn't have to be at x equals 0. It could be at any point. But those are your 4 boundary conditions. Convection on a boundary, meaning if air is blowing onto the surface of a solid, that's not constant temperature, it's not constant heat flux, it is convection. Convection flow, heat flux will equal to the conduction heat flux. Okay, perfectly insulated. Just because something is insulated, that doesn't mean it's perfectly insulated. If it's perfectly insulated or close to being perfectly insulated, we'll call that adiabatic, and the heat flux will equal to 0. Okay, constant heat flux, which is basically if we face a heater to a solid, we put it on, like for example, we put a heater plate on the surface, right, and it's directly connected to the solid, that will be constant heat flux. Therefore, the heat flowing into that solid will equal to the heat flux entering in at point at x equals 0, which is the heat flowing in is conduction. So the heat flux, as we said here, will equal to the conduction heat flux. Okay, and constant temperature. Constant temperature at x equals 0 will assume that the temperature everywhere in the surface is the same. Obviously, these are not the only boundary conditions. There are many more, but for this course, we'll be only covering these 4. An example of an extra one, for example, if a rocket is in outer space, there's no convection there, no conduction. There is radiation. We won't be covering radiation boundary conditions in the scope of this course. But that is it for this class. This is your heat diffusion equation for conduction, and it is a function of temperature. As a function, it's used to find temperature diffusion throughout the solid as a function of x, y, and time. See you in the next class.